Welcome to the annual Bjerknes lecture of the Atmospheric Sciences section of AGU. This lecture today, together with the following lecture, the Charney lecture, to be given by Paul Newman, really represents a series of events that kick off the centennial celebration for the Atmospheric Sciences section of AGU. My name is Jim Hurl, and I have the honor of being the incoming president of the Atmospheric Sciences section. The Bjerknes lecture, I think, as many of you know, is named in honor of Jacob Bjerknes for his pioneering work in developing the basic theory of fronts and cyclogenesis and weather prediction and the development of quantitative models to that purpose. This year, it's a tremendous honor for me to be able to introduce the Bjerknes lecturer, Dr. Peter J. Webster, who is also a recent past president of the Atmospheric Sciences section of AGU. Peter is a professor emeritus of Earth and Atmospheric Sciences at the Georgia Institute of Technology, and currently he is the chief scientist for the Climate Forecast Applications Network. Peter received his Bachelor of Science from the Royal Melbourne Institute of Technology in Australia and earned a PhD from MIT in 1972. Peter's really had a remarkable career with exceptional accomplishments at the forefront of Earth system science, as well as service to our atmospheric and related sciences community. Generally speaking, his research has focused on the dynamics of large-scale circulations in the atmosphere and oceans, with a particular emphasis on the tropics. Most recently, he has concentrated on the application of theory to determination of the predictability of weather and climate in South Asia. He is also the author of a forthcoming book on large-scale dynamics of the tropical atmosphere and ocean system. Peter has received numerous awards, too many awards to mention here today for his contributions and pioneering scientific efforts in our community, but I'll just briefly mention that Peter is the recipient of the Rossby Research Award and the Charney Award from the American Meteorological Society, the Gill Medal and the Mason Gold Medal from the Royal Society, the AGU International Award, and the UN Prince Sultan bin Abdulaziz International Creativity Prize for Water. Peter is a fellow of AGU, AAAS, AMS, and an honorary fellow of the Royal Meteorological Society. Please join me in welcoming and congratulating Peter Webster for this year's Bjerknes lecture.
Well, thank you very much, Jim. I had a realization early this morning, and I went to my computer and looked up Bjerknes for a whole heap of reasons. And one in particular, I met him when I was a graduate student. I went to UCLA with Jewel Charney for the summer, and I met this rather elderly chap, very gentle person, and I tried to convince him I understood El Nino, even if he didn't, but that's my ego. And so I didn't convince him, but I looked up his age of this rather old, feeble man. I realized he's exactly the same age as I am now, so. I say this as a warning, not a warning, a plea that as I'm an old and feeble chap, be nice to me with your questions. What I'm going to talk about today is something that I've worked on really for the last 40-odd years in fits and starts, and it's about the interaction of the extratropics and the tropics. And as we'll turn that around eventually in terms of the tropics to the extratropics as well. And it started off a long time ago. Let me show you my first slide. During the 60s and 70s, numerical weather prediction, of course, was starting to bloom. And we realized, or many people realized, that it was very important to have data from the tropics, because very, very quickly a forecast would become perturbed very quickly. And so there were a lot of observations made, and the Pacific Ocean was in particular, because that's where the nuclear tests were back in the 60s. There was a fair amount of data. So these particular theories that came about were relative to a zonally symmetric basic state. You might think of a symmetric Hadley circulation. And those pictures on the right-hand side there give you the geographic journals or geographic books idea of what the circulation is like. And of course, it doesn't do very, very well. So the more the research continued, a number of dynamical conundrums arose. What the nature of the tropical phenomena relative to extratropical phenomena didn't seem to work. The connection between the tropics and the extratropics was very difficult to understand. So just to show you some historical slides, I'm a great believer that we forget very much about the old work. This is from Herbert Real many, many years ago. And what it shows, his realization that the trade winds were extremely steady, the steadiest of all winds on the planet. And here is a picture of that, whoops, in the Pacific Ocean. And you can see down here, this is Iwo Jima, one of the few vertical cross-sections existed at the time, very, very steady winds. And this was the start of one of the great confusions that we had. And also, there were regions of intermittent westerlies over the equator. And this was unheard of in the sense that if we think of a purely Hadley circulation, westerlies very close to the equator doesn't quite fit with the model that we might have. And here is a picture of the upper tropospheric westerlies. These are from Herbert Real's work. And also, Real also found, if I got the right one, yes, that we have trains of transients that moved into the equatorial regions. This was unheard of. And I have his 1954 book, and it's a delight to go back and read some of the things that Herbert Real found. But in particular, what he said was that the intermittent appearance of high tropospheric westerlies in the equator is foreign thought to the classical views of the general circulation. Yet there is evidence that they do occur, and since flow in the high levels is so unsteady, coupled with at high latitudes between the circulations of the two hemispheres, it promises to provide an important link understanding about the foundations of our general circulation. And this, of course, was a very foreign thought. And this was picked up by Giulciani, who noticed that in the tropics, the blue is convection, that there is a lot of convection with very, very little seemingly thermodynamic structure. These are isotropes, potential temperature, it's flat, like a billiard table, but we still get these convective things. Of course, in mid-latitudes, you can see the troughs and the ridges associated, as we understand, from quasi-geostrophic theory. So the biggest difference comes about by realizing that in the extratropics, and this is a section of density and pressure, that when the two vectors of gradients are offset, you have a baroclinic atmosphere. In the tropics, it's very barotropic. And so this gives a great problem, because when you scale the equations of motion, as Chani did, he finds that in the extratropics, you have very divergent circulation. In the tropics, there's no connection between the upper and lower levels, so we have these very steady trade winds, and we have these variations that Real observed above. And so this was a problem. One of the things I'll bring up later on is that there is an intermediate subtropical scaling that is very important that Chani doesn't mention. So here's Chani. He noted Real's observations, and he used quasi-geostrophic theory to show that what worked in the extratropics didn't work in the tropics. He considered a zonally symmetric model, tried to understand the propagation of extratropical waves from the extratropics, where we know there are lots of waves, to the tropics, where we observe waves but couldn't explain them. And so he made this statement that the picture of the tropical circulation that emerges is quite different from the conventional Hadley circulation. He talks about the rising motion is much more concentrated, and the descent is spread over a large area. But the interesting thing he found or surmised was that the quasi-non-divergent source-free flow acts to transfer lateral influence from the extratropical circulations. And this determined all of the convection at high latitudes. Unfortunately, theory didn't agree. But we'll come to why it didn't in a minute. So there were a whole heap of research topics. One, my favorite is by John Young. And I'm not just showing pictures of people who have passed on today. John is very active, of course. At least he was last week. And so the basic modeling was you have a wave source here, you have some type of westerlies and easterlies, and you ask the question, how far can a mode propagate towards the equator? Can it give you the convection that you notice? Can it give you the convection that was noticed in the very famous Gate experiment in the Atlantic Ocean? And but the unfortunate thing, and I'm not going to go into details, please, there are a number of papers I can point towards, but what it finds is that in this very, very simple basic state, that waves do not propagate. And the waves that can get to the tropics are so low energy, it can't explain those vigorous circulations. So Mencken Mac came along, and he's still active, and he developed a numerical model which has 2 layers, and now we could look at the impact of both latitudinal and vertical shear. And what you find when you force waves here in the extratropics, that the perturbation energy dies off very, very rapidly. So this is further proof, even in a more complicated atmosphere, that you can't have propagation from the extratropics to the tropics. But then if you take that same model and say, well, let's have easterlies and westerlies, let's have complete westerlies or complete easterlies, and look what happens now. And you find that the perturbation energy now transfers across the equator. So you can explain this particularly well if you're interested in critical latitudes and so on, but the point is that the models weren't modeling reality. And this just showed you here that this is a repeat of the same slide, that your perturbation energy tends to be strongest in westerlies. And we might remember too that Riehl made the observation that there were equatorial westerlies. So going back to Herbert Riehl. And so Murakami and Unanaya did a nice plot of the yellow areas are easterlies and the perturbation kinetic energy is in the contours. And what you find for these 2 months that they looked at, that the perturbation kinetic energy was much, much larger along the equator where you had westerlies. So this was the first realization that, when you have westerlies, locally you have much more perturbation energy. And this is a paper that Phil Arkin and I did many, many years ago. And when you look at you plot the perturbation kinetic energy against the wind, local wind, and you find that energy increases substantially into the westerlies. A very high correlation. So at this stage, Jim Holton and I thought it might be an interesting thing to see what would happen if you were to model now, not with a zonally symmetric basic state, but with a basic state that varied with longitude and latitude. So in other words, there's what we termed a westerly duct or equatorial westerlies. And then, depending upon where you set the forcing, this is some perturbation forcing here, you can get a propagation through the westerly duct, or if you have it further to the west, you don't, because you encounter what are called critical latitudes. And in fact, if you have a stronger westerlies, you finish up with much stronger propagation. And so what we have now is a pathway for extratropical waves to move towards the equator. One question you might think about at the moment, for later on, is why do we have equatorial westerlies? It's just happen chance, like a standing wave, a mountain wave, or a heating wave, or something like that? Or is it something maybe a little more fundamental? And the other thing, too, is that the tropics aren't made up just of easterlies and westerlies. They also have an enormous amount of vertical shear. These are two sections along the equator, one for June, July, August, and one for December, January, and February, where the red bits are westerlies, and then we have easterlies. So we get an enormous amount of vertical shear. And so what is the impact of the vertical shear? And just as a very quick thing, that one nice way of looking at the world is through potential vorticity. Think of it just as regular vorticity. This is isentropic potential vorticity. These are the lines of isentropes, constant potential temperature. And if you move from one region to another, you can generate relative vorticity depending on the stability, or you can change the stability. And so this is a very nice way of looking at life. And in fact, when you look at the, on the left, the mean potential vorticity, what you can find is that in the tropical regions, it's slightly higher, but up in the high latitudes, it is very large and very, very strong gradients. That will turn out to be very important. And when you look at the variance, the variations on a sub-monthly basis, you find that there are channels of perturbation, potential vorticity all the way through here. But when you look lower into the atmosphere, now looking at 850 or 350, but 850 millibars, that here, what you find is there's no perturbation, potential vorticity at all. So these waves are propagating, but they're not propagating downwards at the same time. So if you do look at this cross-section here all the way through the westerly duct, and what you find, if you look at the sort of X is here and Y is here. So you have to sort of switch these around in your mind a little bit. But what you find is that along here, this is the structure of the westerly duct. You can see the westerlies. And here we have what we'll call the easterly dome, if you like, a region of deep easterlies which exist. And if you look at the potential vorticity, and you can see once again, you get these corridors through here. Now I'm going to look at this base point here and do some correlations. If I do that, what I find, looking here in the upper troposphere, is that 3 days before an event, you can see the lag correlations very, very strongly moving through here. So there's very, very strong observational evidence of upper tropospheric propagation. Yet, in the lower levels, one doesn't find that at all. So if you now go to looking in the cross-section and looking at the lag correlations now in the vertical, what you find is that the waves tend to, 3 days before, they tend to rise up over this easterly dome and fall, and then fall into the southern hemisphere. So there's a complicated interaction. Now, I'm going to show you two quick examples of the penetration of these Rossby waves into the, and the first one I'm going to talk about is in the Asian monsoon region in June, July, and August. This is one snapshot of the incursion of potential vorticity. This is a breaking wave here. It's gone all the way across South Asia. It turns out that's very strongly tied to the quasi-biweekly oscillation that was first found by Krishnamurti way, way back in 1970. And it's also in a paper by Sebastian Ortega in 2017. And also, we're going to look at very quickly at the generation of convection in the eastern equatorial Pacific Ocean. This is what the climatology on the upper troposphere, if you'd like, but in terms of potential vorticity, you get the westerlies here, westerly duct, and even in the Atlantic Ocean, a second jet. In the southern hemisphere, we have a jet stream to the south. And when you look at the potential vorticity, you get very, very strong gradients dipping down into the tropics. And in the summertime, you get these, this is the monsoon gyre, if you'd like, upper tropospheric. And this region of westerlies, you get these incursions of flux. So this is the summertime, and you watch these breaking things here, and you can see these streamers of potential vorticity moving across out of the Pacific Ocean. This is downstream of the westerly jet stream here. They come in here and they break, and I'll explain about breaking in a few minutes. and they stream across, and with that, they bring in variations in the monsoon rain at about 2-week periodicity. So if you were to correlate relative to these incursions here, and composite relative to these events, this is the type of thing you get. And this is and the upper right is the potential vorticity, and the bottom diagram is the variation of precipitation and the 850 millibar winds. And you can see coming down through here, these events as they move across, and so on. So this is very useful because it shows that the tropical weather, at least in the summertime, is a strong function of incursions from higher latitudes. Also in the boreal winter, this is just a snapshot again from Funetsu and War, and it shows you these breaking frost waves. Notice it also from the southern hemisphere, all breaking in this chaotic region through here. So this is the same type of movie, but now for the winter time. And if you watch these incursions here, and I might add that these incursions have been found by Georgopoulos and Weichmann, a number of people, to be strongly associated with convection forming in the Eastern Pacific Ocean, and to do with the atmospheric rivers which go into California. So these are sort of beautiful to watch. I'm sure this is something that in the 1960s people would like to sit back and think about different times. But here's a series of 4. This is one breaking wave. Now the yellow part here is OLR less than about 210, so it's deep convection. And just 4, you can see that moving through. The red area is vertical motion upwards. And Funetsu and Moore did a very nice explanation of what is happening. This is the PV trough moving through, the uplift on one side, the downlift on the side. And if you scale the equations of motion for the subtropics at about 20 degrees and not at the equator as China did, what you find is that these are almost quasi-divergent. So you get the possibility of these modes forming. So in a sense, we might ask the question that even though China didn't know about selective propagation into the westerly duct, what he did know was that these big troughs were causing problems or convection, I should say, in the equatorial regions. So one of the nice things about using potential vorticity for those involved is that the very famous paper of Hoskins et al., Hoskins and McIntyre, back in 1985, allows you to look at the potential vorticity field and determine the dynamics. And this is what, in a sense, what Funetsu and Moore have done here. So let's think about what causes all of these things. Michael McIntyre is an iconic figure, he's a very interesting man. He is one of my favorite people, and when Sebastian Ortega and I published our first paper in 2017 together, it was 17 pages double-spaced with about 6 diagrams, and 19 pages of single-spaced comments came back from one Michael McIntyre. But it was okay because we answered Michael's comments, and he said, yes, very good, yes. And then it went down to 17 pages for his second lot of comments, so I guess we improved a bit, but it was a very, very fruitful interaction. But what he did, he found 2 types of things in the tropics, in the exotropics. When you look at the polar vortex, he found regions of strong potential vorticity gradients where you have jet streams, and then regions where Rossby waves break. And so what we've tried to do is, sorry about this, but this is Michael's jigsaw puzzle, and this is sort of our solution where we try and join these 2 things together. So this might only have been a 15-page critique on what I'm saying now, but we'll see. What you find is that the Rossby waves breaking in the westerlies, in the big, broad westerlies across the Pacific Ocean, lead to an advective equator flux of potential vorticity. It's very important. So they're serving a purpose. They're sending potential vorticity towards the equator. However, if you look further west, where you have strong divergent circulations, be it the monsoon or the heating associated with Indonesia, you have strong divergent populations, gradients, circulations, and they are pushing potential vorticity poleward, I'll get this right. The waves send potential vorticity towards the equator. The divergent circulations push potential vorticity towards the pole. And the concentration of potential vorticity in the divergent circulations gives you the jet streams. The jet streams, on the other hand, are where Rossby waves form. They move to the east and they break. And why they break, I'll give you a clue in a minute. So the question is, are all these fluxes related? Now, this is my one equation. Just as to show you the type of potential vorticity surfaces, and we're moving a column down from one region to another. And if we have a velocity v, which has a normal component, we finish up with the flux of potential vorticity. All that just to say that. But what do these fluxes look like? Well, there's one thing I should mention, very important. Haynes and McIntyre came up with what's called the Impermeability Theorem back in the late 80s. Turns out to be an enormously important formula. And it says simply that there are no sources or sinks of potential vorticity between isotopes that do not intercept the ground not being an isotope. And PV flux across the isotopes cannot occur. And you play around, and if you want the details, go to Ortega 2018, and what you show is that the integrated flux of potential vorticity equals 0. So in other words, that which fluxes north has to flux south for there to be a balance. And so what do these fluxes look like? This is the observed mean fluxes for, look, we've seen this diagram before. This is now averaged over January. And you can see here extending waves into this region through here. And that's one day, but this is for the mean. If you look at the fluxes across latitude lines, the first one here is across 30 degrees north, and we have northward fluxes, southward fluxes, northward fluxes, southward fluxes. And within the error of the observations, they balance within about 2%. So what is flux north is flux south. And the same for about 10 degrees north. And this is for July. Now the distributions have changed, and now we look at the flux across 30 degrees north, northward, southward, northward, southward. And the southward fluxes here are to do with those filaments that we saw before in the movie. So here we have then an interesting application of the impermeability theorem where we flux north and flux south. And so one might think then that the jet streams, the divergent circulation, and the westerly extension regions are together. So we can look at a couple of experiments if you'd like. This is in a paper some months ago. And here we have some type of heat source through here. And there are two types of, if we assume a zonally symmetric basic state, that everywhere is either northward or southward. Here we would have north in the upper troposphere, south in the lower troposphere. If you insist on zonal symmetry, the only way you can have that is if the flux of PV is everywhere 0. And that's the zonally symmetric sort of held type solution. Important, but for what we're doing, not particularly useful. However, if you have if V has a poleward, what it really says, and if B has a poleward component, there must somewhere be a southerly component to balance the potential vorticity. And there's an experiment that we did, which was with a heat source at 30 degrees north, and you finish up with fluxes in this region, very, very similar to the type of things we had before. Strong flux near the monsoon, diluted fluxes further north. But the interesting thing, even in this simple experiment, what we find, each one of these is some time apart. We get what we call recursive propagation. In other words, as we saw in those movies, you get one breaking wave, one breaking wave, one breaking wave after another. Each one is different, as you might expect in a nonlinear system, but the impact overall is much the same, the fluxing potential vorticity southward. So, might think of a very simple jigsaw puzzle that we have here, where we have Q being the potential vorticity, have a polar vortex. This is the type of system that Michael McIntyre looked at. And then we say, what about if we add a heat source? Now we have a strong divergent circulation, and that bunches up the potential vorticity through here. It forms a jet stream. The jet stream moves, the Rossby waves move into this region through here, and they tend to move south. Now, the important thing is that they're not looking, the Rossby waves moving through aren't looking for a westerly duct to propagate through. They are forming the westerly duct. It's a very important little point here. So we have a divergent circulation, and we can see now that the divergent circulation, westerly jet stream, Rossby waves, and then the production south. So breaking Rossby waves, this is a result of a numerical experiment we did. In fact, you see, this is the details of the monsoon experiment. And you see over a 4-day period a breaking wave and how the filaments tend to extend almost zonally and all the time pushing potential vorticity north. This is relative to a heating source, which is here, producing that jet stream here and here. So why do Rossby waves break? And Rossby waves break because a Rossby wave, in a sense, is a nice balanced flow. But if it moves into a region where it is distorted so that the balance there is no balance, what you finish up with is an extended wave, and which is no longer in potential vorticity balance. So when you look at a jet stream, the central zonal speed is here, and it decreases towards the east. There's also a north-south gradient of the zonal wind. So here's a wave, and it's going to move into this region here. And what's going to happen? It's going to break, and it's going to, because it finds itself, is one explanation, that you can go back to some very, very fundamental wave theory, which was introduced a long time ago by Francis Bretherton and James Lighthill. And what you find is that as you move this wave along through here, it is going to feel its surroundings, and the wave number is going to change relative to the east-west variation of the flow. So what you find is that the flow tends to bunch up. So here, a long wave becomes a short wave. And what I don't show also is that as you do this, the energy density, so to speak, tends to increase. So this becomes, in this region here, highly high dense energy, and as the wave tends to move forward. Also, in the lateral shear, the wave tends to shorten in the north-south direction and extend. So the wave is completely distorted as it goes into this very, very strongly varying flow. Similar principles occur elsewhere on the globe. You can explain in the same way, this is now the great waves, the great cloud bands of the southern hemisphere. There, this is a little diagram here, you can see the jet stream, you can see the trough, and if you look back at those movies, you'll see breaking Rossby waves all the time, moving up in towards the tropics, and moving streamers back and forth into here. And by the way, this just shows you how much the east-west wind changes as it moves through. So the wave is just distorted and tends to break. So I can summarize quite simply with this really very simple view of how the world works. And so one starts off with divergent circulation, the concentration of isotopes. Think of them, if you'd like, as, you get the jet stream, and the jet stream produces Rossby waves, and Rossby waves move into that distorting region where they break and have very, very strong flux of potential vorticity southwards. So what you have is then the balance of the poleward and the equatorial potential vorticity. But the interesting thing is that we have a divergent circulation, and everything else is handled by Rossby wave dynamics. And this was a very, very foreign thought 20, 30, 40 years ago about how the tropics are maintained. So in other words, the westerly ducts are necessary conduits for the balancing of potential vorticity. As I've got about a minute or two to talk, there are a couple of other things that we might want to consider about global balances. Clearly, if you look at this diagram, it works for the southern hemisphere, it works for the northern hemisphere, and therefore, in a sense, this whole impermeability theorem works for the globe. But there are some peculiarities that we have that we've never understood, and one was pointed out by Graham Stevens some time ago, about 2 years ago, 3 years ago, about despite the great differences in cloud populations and in geography between the southern and the northern hemisphere, the top of the atmosphere radiation balance is much the same. The southern hemisphere albedo is much the same as the northern hemisphere albedo. And this, to me, is an interesting problem. The second one is when you look at precipitation over the northern hemisphere on an annual basis, and you look at the precipitation over the southern hemisphere on an annual basis, and if I told you that they are within balance to 1% as best as we know from CMORPH, that might surprise you, given the great geography differences we have between the northern and the southern hemisphere. So, and a third point is that why is it when we have orbital forcing of climate variations on the very long term, it's a decrease of radiation in the winter hemisphere. Of course, over a year it's balanced. There's no change to the total radiation arriving in the planet. But why should one hemisphere drive a global ice age, for example, or a warm period? Why? One would think that you would get the opposite poles of an ice age, hypothermal south and a cold in the north. But no, you don't. So there are some overall constraints in these three examples I've mentioned, which I think that it may be worthy to start thinking in terms of impermeability from a, excuse me, from a potential vorticity point of view, which may help us explain some of these curiosities that we find. Thank you very much.
I think before questions, I would like to present to Peter our certificate for his lecture, and also introduce myself, which I forgot to do. I'm your current president of Atmospheric Sciences. So can we take a picture here?
Reason that we voted for Joyce to be in charge of atmospheric sciences, she's very clever. She insisted on giving me the certificate before you asked the questions in case I failed. So.
All right, so we have ample opportunity for some questions of Peter. This is a really big room, so please speak up to the best of your ability, and I'll ask Peter to briefly summarize the questions he received. So, questions? Yes.
So, Peter, what does this mean with respect to El Nino pulsing?
I missed the last word.
Oh,
Pulsing.
or El Nino in general, timing.
Yeah, I must say that I haven't thought too much about interannual variability. I've been concentrating on the shorter term. But one of the, I would put it this way, when you look at those movies and you see the variability that is occurring on the shorter time scale, and El Nino finds itself in a rather hostile environment for good initial conditions. But I will say one thing, though, that as you do move into El Nino, the divergent circulation does change. The Asian jet stream moves to the east, and the Atlantic jet stream moves east. And of course, the amount of perturbation energy in the Atlantic and the Pacific, normally bigger in the Pacific than the Atlantic, just change sign, anomaly, yeah.
Peter, so my question is along the same line. You emphasize the westerly jet, but we know the westerly jets are not stationary. They are actually changing. During El Nino, they change.
Yes.
During climate change, they change. They have trends. And they are very much tied to the Walker circulation. In fact, that westerly jet has to do with the Walker circulation. And we know the Walker circulation are changing. In fact, common model says one way off, way
Yep.
says another way. And that actually brings back to the Bjerknes feedback mechanism, which is broader than Enso. So I would like you to comment in terms of the change in the Walker circulation that now
Yep.
we know, in terms of what is going to happen with regard to whether you get more extratropical influence on the tropics or the other way around from the monsoon.
Okay.
Please briefly summarize.
I've been, well, my summary will be about 19 pages. Have a joke. What Bill is asking is, we have the Walker circulation, and we know that it's tied strongly to El Nino, and it varies during El Nino. What does this do in terms of, I think the things I've been talking about? And I would say that when you've, question before, that when you change the sea surface temperature distributions, you do change the divergent circulations in the northern direction as well as the eastward direction. And you change the concentration of isotopes, potential vorticity, and you change the position of the jet stream. So I think that's fairly okay. The question I used to have, what was the cause of the equatorial westerlies themselves? Was it the Walker circulation? In other words, can you explain everything in terms of standing waves? In other words, Walker circulation, easterlies here, westerlies there. I've come away from that conclusion now, and mainly in terms of all you have to do for the Walker circulation is change the divergent circulation north and south, and you therefore change your avenues of where your return potential vorticity will be. So I think it fits in. You could change the boundary conditions to give you El Nino if you'd like, and I think you'd quite nicely change the location of the jet streams.
Which way, do you have any idea which way things going to go? More isotropical influence or more tropical influence?
No, I don't know that. But I would say that the location of the PV incursions will change. They'll change principally during El Nino to the Atlantic, and during La Nina more to the. And I think you can tie that to where the jet streams are going to be. If what I'm saying makes any sense, you start off with the divergent circulation, which is to do with the heat sources and hence sea surface temperature. You change the location of the jet, which becomes unstable. and, and also the strength of the Rossby waves coming off. I guess. I haven't thought that through too much. Yep. Yes. Yep. Yep. The comment was, and it's a good one, that not only do the frequency of these waves change with El Nino, the phase of El Nino, they change with the phase of MJO, and that is true. There are some interesting papers coming out about the role of the extratropics on the MJO. And, you know, I go back to comment before about, of all the places to initialize the model and understand the physics, ENSO and the MGO are in pretty bad locations by virtue of the influence of chaotic phenomena. So sorting that out is going to take some time, but I think that's a very, very important point.
If I understood correctly, you were saying that the Rossby waves break when they bunch up. What causes them to bunch up?
What's it? Yeah, what causes the Rossby waves to bunch up? One of the great mysteries of life is what happens to a Rossby wave as it moves through a longitudinally varying basic state. And we've written a lot on this. And what happens is that as the wave moves eastward out of the jet stream, it encounters du dx, which is negative. And this, according to the kinematics of waves, tends to compress the wave. And this is very important because as you change the wave number, you change the group speed. And therefore, you tend to change the concentrations of energy associated with that wave. So as that wave moves out through here, it tends to be, as you can see here, it tends to become a very concentrated wave. And it's very, very hard, in my simple way of trying to understand very complicated nonlinear variations from a very linear perspective. You finish up with a concentration of waves. You have a group speed which is getting smaller. And at the same time, the variation of the north-south wind tends to compress the wave in one and extend it another. So the nice, well-behaved Rossby wave, if we all think about moving through a zonally symmetric basic state, tends to become very, very complicated and convoluted. That's my guess. I'm not sure.
Okay, we had a question against the wall first. Yep.
I'm sorry, I can't hear you. Oh yes, very important. When you look at the long-term averages, the strength of the westerlies in the Atlantic are not as extensive or as strong, except, of course, as we were saying before, during El Nino, when the jet streams change and the divergent flows change. So, no, it's very important. It's important in the South Pacific. I think we have a good chance of being able to understand the great cloud bands by virtue of understanding the potential vorticity flux. So no, it's the main avenues of communication between the tropics and the extratropics. And if you didn't have them, you get such a concentration of potential vorticity in the poleward regions, you'd have an infinite jet stream. So, yeah.
Maybe one more question.
Yes. You know, I really wish we had a microphone. I tried very hard to hear you.
I was just saying that at the lower level, there's a wind evaporation feedback.
Yes.
Which produces the wind evaporation feedback both towards the equator to the west.
Yes.
So it needs to be treatment.
Yep. Yes. Yeah, and it's a good point too. The question was, or the comment was, there is a lower troposphere, and which I've essentially ignored. The only way that I speak about the upper troposphere is it's invoking of convection by virtue of the divergent circulations. But yes, there are very, very important lower tropospheric things that you can't explain all convection in terms of propagating Rossby waves. You can explain a lot. There was some nice work by Dave Raymond and co. and Chris Bretherton have shown the importance of the feedbacks and so on. You too. And the issue is, yes, the way I would look at the lower troposphere is it sets up the divergent circulation, and very importantly, that you get the feedbacks.
All right, we will begin the Charney lecture in about 7 or 8 minutes, but first, please join me again in thanking and congratulating Peter.
Thank you.